We will wrap up the course. A couple of examples on mass transfer. Even though for the exam, I don't really anticipate that there would be any big problems on mass transfer. We have not given any assignment sheet. We have been thorough with the basic definitions, the relationship between the fluxes and the mole fraction gradients and so on. That should be sufficient. These examples are mainly to illustrate the use of the relations between the fluxes. So there won't be any really physical problem that you would have to solve in a big way in the exam. Although I remember a couple of years back I asked him to find, for instance, the mass flux of a component, mass transfer. It was just, you've already know how to calculate rho v dotted with NVA. This is just a rho A VA. So it's a very simple application. There might be one or two short problems like that, but not any big problem that you have to set up and solve. So they're taking the example of the Stefan cube, which is a very famous example, which is used to measure diffusibilities, both binary as well as ternary and so on. So the Stefan cube basically has a rectangular or a cylindrical cube. We consider a rectangular cube which has liquid. Basically, the liquid is the one that is diffusing. What we have here is A. It's good to often assume, good assumption that the gas, which is sort of fluid, like an inert gas, it's not really going to dissolve in A to a large extent. So what we are having is that liquid level, which we can assume to be maintained at just the top of the cube. So this is liquid, and so here it's basically A. So sort of evaporation diffuses into the gas, which is be A and B both. It's like a gaseous diffusion, A diffusing in a stream of B, right? So, the basic equations are the continuity equation, which I have here. We assume one-dimensional diffusion, which means that d by dz of CABAZ is equal to 0, and P and T are constant. And if I assume ideal gas loss, this would mean that the total concentration Ca plus Cp is also a constant, uniform throughout the system. So I can write this as C times d by dz of Xa 0, which means that Xa times dAz, the z direction, z equal to z1 and z equal to z2, equal to some constant, let's say C1. So part of the problem is already solved. The other part comes from writing an expression for NAZ. And NAZ we know is CA which can be written as Ca times BAZ minus B star Z. That is the Z component of the molar average velocity plus Ca BZ star. Once we got to the solution and explain how to calculate the diffusion, we will explain the whole scheme of the system of equations. This might appear like suddenly it has come from just a definition and how this is going to help us in the solution. And we'll see how it is going to help. But where it is coming from, what is the basis of introducing this all of a sudden? What are the other equations that we have to take into account in a general problem? We'll come summarize that after this problem is solved. And so anyway, you should not have any doubt with this expression. It's just a definition of NA, that's the convective flux. It's often regarded as a sum of a diffusive flux plus another convective flux which involves the average velocity. The convective flux of A, and that can be decomposed into two. One is a diffusive flux plus the remaining, which is also a convective flux but calculated using the molar average velocity. So this is straight straightforward from just the definition. So now, here is where I would introduce the fix first law, and then I have this which I can write. So this could be again CXA BAZ is equal to CXA BZ star. Now if we look at what BZ star is, BZ star, the Z component of the average, molar average velocity is XA BAZ star plus XB, which is 1 minus XA BBZ star. I'm sorry, no star, that's just the individual species velocity, the Z component. But we are assuming stagnant B. If the B is flowing on top of the tube, inside the tube, it is basically the diffusion distance, the diffusion length. Here is Z2 minus Z1. We assume that in that region, it's not a perfect approximation. You can relax that approximation. Many have solved the Stefan problem in 2 dimension and so on subsequently. This is the simplest approximation we can make. So the stagnant B within the diffusion length, you get this to be 0. So we are getting that BZ star is again XA BAZ. So what we are actually getting is we can cancel the C, and so what we get is XA times, or rather XA BAZ times 1 minus XA is minus BAB BXA by BZ. Right? And I know that XA BAZ is a constant, so if I substitute that here, I get minus DAB dXA by dZ is, because that's important to know, because when I have to integrate, I want to know what that is, and we've seen that from the continuity equation for species A, right? So we are using that along with the fixed first law effectively, and getting this important differential equation in so dXA by dZ is equal to minus C1 by DAB times 1 minus XA. So the first order differential equation in XA with respect to Z, it can be very easily integrated, separable in this case, easily separable and can be integrated. You always have to worry about that we introduce an integration constant, right? And then on top of it, I have the C1, which is a product of XA times BAZ. I also don't know what it is. I only know that product is a constant. So we have to find that also. So it is clear that if I am able to specify the value of XA at the 2 points at the ends of the diffusion length, then I have 2 conditions, so I can find the constant, right? So let's do that. So we now integrate this, it will be XA by 1 minus XA. Suppose I integrate from, I can find C1 first by simply integrating this from XA1 to XA2. And then I have minus C1 by DAB dZ, Z1 to Z2. So this is minus logarithm of 1 minus XA, then we get between, and this is minus C1 DAB times Z2 minus Z1. What do I get rid of the minus signs on both sides? So we get log 1 minus XA by 1 minus XA1 times DAB divided by Z2 minus Z1 is equal to C1. It's a very important relation. We find this constant C1, right, as, now can we determine C1? Yes, if I know the diffusivity, if I know the diffusion length, and if I know the value of the mole fraction of A at the 2 points, right? One on top of the liquid surface and another right at the top of the tube, then I can find C1. Right? So C1 is known, right? So then I can now integrate to get the profile, the composition profile. I can integrate it by 1 minus xa. I can integrate it from any one of the points to xa. So I have now changed the dummy variable of integration. So you follow the way I do things. Of course, rather than integrating and then calculating the constant, I am directly integrating from one of the ends, which is a matter of choice, to an arbitrary point, right? So I don't want to keep the same variable, so I want to distinguish it. So I am using a dummy variable of integration. This would then be minus C1 by dAV. This is simply going to be Z minus Z1. So then I again have minus log of 1 minus XA by 1 minus XA1 is equal to minus C1 by dAV. Z minus Z1. So I can get the profile as there are many different ways. I can just leave it like that. So this can be written as 1 minus XA. I like the final expression, which is there in working like it, somewhat derived from this. What he has is 1 minus XA by 1 minus XA1 is equal to 1 minus, because he's actually writing an expression for C1. Substituted expression for C1. So then I have another logarithm coming in, a whole bunch of other terms. So if I rearrange, then I should get this. This will give me the composition. So you can easily plot it and see how it would look like. XA2 will be typically 0. I guess, because we see that at the top we have usually pure V going past, so we take XA2 to be 0, but it can be small mole fraction, can be there, can be a mixture of A and B. But anyway, so we've got this. Are there any questions on this? Yes.
VAZ as constant.
No, we are not taking it. It is dictated by the continuity equation. There is one-dimensional diffusion. So only Z direction we consider. So the gradient, the divergence of CA, BA equal to 0, that's the most general form. We are considering steady state, no reaction. So this is what you will get. And for constant C, which is, since the equation differential constant, C is fixed. So, assuming ideal gas mixture is clear, C equal to P by RT, right? So, P and D are fixed, the total concentration is fixed. So, I can write this. This is coming from the continuity equation for A.
So, then as XA decreases as we go further away from that solution, VAZ
it will be. It's a problem. That itself shows that it's a problem because VAZ is actually becoming very large. So it's not really a very, so when XA is 0, it is really not applicable right at the top. Right? So this is one of the limitations of the simple one-dimensional model. So the basic problem is overall completely assuming that V is stagnant. Right? And also one-dimensional. So if you don't do that, then you get other terms in the continuity equation that will balance this. Clearly what he is saying is very true. If we are saying this is constant rho, then I am saying also that most likely XA2 would be 0. That would seem to mean that the velocity has become actually infinity at the top. It is really quite unphysical. Right? So that's an approximate. This shows the limitation of such model. But this is the simplest zeroth order model that was attempted. Since then, even as early as 1976, there has been a two-dimensional model showing that in fact that the gas B is not quite stagnant, and the effect of the recirculation and all that have been well studied. This is the simplest that we can do, right? So this is the point, and so this is more convenient. This model is very useful for experimentalists because it will give directly the diffusion coefficient. Otherwise, we're studying the phenomena, but you have to solve a couple of momentum equations and so on to get a diffusivity seems very much of a work to do. So for experimentalists, this kind of a model seems to work, and they used it to calculate diffusivity, right? So we'll see now how that is done, right? So I have an example which will illustrate this. Very quick example. Just write down the solution. So what they have was from Lightfoot in section 82. What he has is the liquid is carbon tetrachloride, and he has an oxygen. It's basically the A is carbon tetrachloride, CO4 plus O2 is the gas phase. And then he is given the pressure is 725 mm mercury. Temperature is 0 degrees centigrade. Right? And then it is found that NAZ, that is the steady state flux, which is doesn't vary with Z, that has been found to be measured. So this is what they measure experiment. Keep the temperature and pressure fixed, right? And then let the evaporation begin, and then after it has reached steady state, measure the flux of A, right? So, and that has been measured to 7.6 times 10 to the minus 9 gram mole. This is the CCl4 centimeter square per second. And then XA2 is taken, which is 0. And what is also given, the saturation pressure of A, that is CCl4, at 0 degrees centigrade is given to be 33 mm Hg. Some special cases the Ravi's law is then used to calculate XA1 right at the interface, that we assume, it may not be exclusively of the try to measure it, but assume that roughly that would be given by what it would be equilibrium with this is actually a binary gas phase in equilibrium with a liquid. So Ravi's law will simply give PA, the partial pressure of A. XA1 is not a liquid because normally X is used for liquid. XA1 is the mole fraction of vapor just at the top of the liquid. Right? XA1 is PA sat by 3. So that is 33 by 760. So we know XA1 that's given to be quite low, 0.044. So what is there is the expression for the diffusivity is right here. Right? Diffusivity is right here. DAB is what I want. Z2 minus Z1 is given. So Z2 minus Z1, this whole length is given to be 17.1 centimeter. That is the region in the tube, right, above the liquid. Right? So that is what is given. And then we calculate N is given. N is actually CA times PAZ. Right? So this is actually the XA times PAZ. Now XA2 and XA1 are known. So this can be written as C times XA by C. This is NAZ. This is experimentally measured. And C I have to calculate. So C can be easily calculated. E by RT, ideal gas. So P is 755. I don't know, you have to check the units properly. So I think I put this in terms of atmosphere. So 755 by 760 by R is 0.082. converted. If you substitute all of that, then I get a value for DAB. You can check this calculation. DAB turns out to be 0.0621 centimeters square per second. So are there any questions? It's a very simple illustration of the idea. So you can use it to calculate the diffusivity. So there are no questions. Let me discuss quickly one other point where convection, this here it is calculate actually the velocities. So the fluxes are given. So the velocity at the top, you cannot calculate. So it will going to become infinity. But velocity, typical velocity, somewhere the middle of the people calculate, you find that it's actually quite low. And now what I will take is maybe different examples where there's convective effects also. We take the problem that we considered earlier, that of a falling film. We've already considered cases of film falling down an inclined plane and so on. So here I have to consider film falling down a vertical plane, along a vertical plane. This is the ball or plane, and I have a liquid film that is falling, flowing by just gravity. We have already solved this. So we call this liquid as B. And then I also have on top of the flow problem, I also have a gas A diffusing into the falling film. Right? So A is diffusing. The major assumption is a dilute system, dilute absorption. And then we also assume, good approximation, that convective direction, this is the origin, so this is X and this is Z. Z is the vertical downward direction. Convection dominates in Z direction and diffusion in X direction. The flow is in the Z direction due to convection, the forced convection because of gravity, pressure difference and so on. We already have the formula for the velocity profile, right? But we assume the gas diffusion effects dominate in the X direction. The convective effects can be assumed to be negligible in the X direction, right? So that is a basic assumption. We know that Ez is V max times 1 minus X over delta the whole square. We've already got this. The delta is the thickness of the film. Now we want to look at diffusion of A. Let me do the Fick's second law, which will take the following form. So we get here dz dWA by dz is equal to dAB. I'll assume diffusion affects the dominant only the X direction, so I will simply have this. Of course, dz is a function of X. Now, what are the boundary conditions? Boundary conditions are at Z equal to 0, that is at the top of the film. But WA is the weight fraction of A. We can assume that the weight fraction of A is 0. So right at the top of the film, the gas hasn't yet started diffusing into the film. Right? So, and then at X equal to 0, we assume that WA is given by some quantity WA naught, which refers to the solubility of A in the liquid. That's somewhat similar to this at the interface. Right? So at X equal to 0, then at X equal to delta, we take a dWA by dx is equal to 0. That is simply showing that because this is an impermeable wall, so A cannot diffuse through the wall. So the flux is 0, which would lead to the gradient of the weight fraction being 0. So there are certain simplifications that are done, and the first simplification is that it is assumed that the gas does not penetrate far enough into the film. So effectively, the A, because you can see that the no slip condition means the velocity is 0 on the wall, right? So if the diffusion length is a very small fraction of delta, the first approximation that is done is Bz of x is approximately equal to D max. Because over the length where diffusion is proceeding, so the maximum velocity is at this point. So we assume that approximately it will remain more or less the same over the region where we are going to consider diffusion. So that's a simplified solution, right? And further, because the diffusion length is effectively the length, thickness of the film is much larger than the diffusion length, this condition is also replaced by WA at x going to infinity equal to Z, that means state. It's just a convenient of dealing with this boundary condition rather than with the finite length boundary condition. So this is also an approximation to the actual boundary condition. If you put these together, you will get quickly go through that and we will discuss solution. And the solution method is very similar to the similarity transformation that we did for the boundary layer pH. I don't want to go into the detail, but what you get is actually what you introduce. You can easily go and check what is there. I had the following. In fact, a more complicated equation. You have to compare it with this. So in there, you can see that we introduce an eta similarity transformation, because y square root of E naught by mu x. And here, the analogous transformation is eta into x. You see the second order term here is x, right, by square root of 4 dAV times V max times 6. Right, so similar transformation will then lead to an equation which is actually d square WA bar by d eta square. So the bar here refers to the WA being now expressed as a function of eta. So what is actually a function of two variables? Becomes expressed as a function of a single variable eta, which is of course a function of x and z. Right? And this in fact can be very easily integrated. And the final solution is in terms of an error function solution. If you put all the boundary conditions, what you get, WA equal to WA naught times 1 minus the error function of eta. And then the error function is of course defined as 2 over root 5 equal to eta e power. You can easily actually work out the solution and not going to go into the details. You can sort of solve this error function in an effectively the 2 over root 5 takes it upon the fact that error function will actually tend to 1 of any function, of any variable, as the value of the variable goes to infinity. So basically, you can easily verify. But when you plot error function of eta, it looks something like this. We multiply by +1 and -1. So you sort of get the solution. So it would be interesting to plot. Version level doesn't give a plot of how it would look like as a function of x and z. Right? And so this is the solution. So you can then go and calculate the mass transfer rate across the interface. Right? The mass transfer rate would be integral minus OA dA dotted with n dA. Then I'm not going to put n here, so I can look at A diffusing here. So across the interface, when n is clearly the outward normally would be minus EX. A as dy dz. So the whole point is how he calculates rho A dA. Look at words for Lightfoot. So we are not calculating the velocities directly. Now rho A dA, what I want is the x component. So that is a you have to understand that the diffusion is dominant in the x direction. So, but actually what I want, rho A dA dotted with Ex would be rho A dx. And so the way he calculates it is effectively write it as rho A times dx minus dA as the, minus bx plus rho A dx. Right? This is just a definition. This is a diffusive mass-based diffusive chemistry. The mass average velocity. X here refers to the x component plus an additional term. And he says because the convection is the x component of the convective velocity is very small, he neglects it. And so I can then write this in terms of the fixed law as minus rho dAV dWA by dx, evaluated of course at x equal to 0. And then I can calculate it using this Euler function solution. So it's a bit complicated. So as I said, this is not really going to be covered in the exam. You just need to know how, the basic idea here is how the fixed law comes in and how it is helping to avoid having to find the velocities directly. So that's something that we keep avoiding. So if you want to really confront having to calculate the velocity without having to bring in the fixed law, then you have to propose a momentum balance for each species, and those equations have to be solved along with the continuity. So when you are trying to do just with the continuity equation, you need this fixed law, which is itself is very approximate, right? So, and then we don't know how to handle the velocities directly, so we always have to make some approximation, like it's a stack and film, or it can be neglected and so on and so forth, right? If you really want to address the problem of mass transfer directly and in a comprehensive manner, then you cannot simply stop with the continuity equation and the fixed law. So you have to go into the momentum balance. So we really don't have the time to go into all that. Now, given only a basic idea of the phenomenon of diffusion, basic ideas in terms of these species velocity and the average velocity, and looking at diffusion as coming out of the difference in these velocities. And then we looked at different diffusion fluxes and the role played by fixed law in solving some of the simple problems. But if we really want to look at more general problems, then we have to bring in the momentum balances. Right? So, are there any questions on this? So, the exam will cover all of what we have covered in this course. And again, it will be closed book and notes. And I think by now you would have easily realized that whatever formulas required by and large would be given. Some basic thing like the general form, the equation of motion, and so on, you should remember. Right? The basic form, not the component form. That would be somewhat useful. Other than that, anything with Cartesian, the basic vector and tensor operation, you should remember. The dot product and the curve and other so on, how to construct it, right? For the curvilinear coordinates, you should know how to do it given the gradient operator and so on, but the general formula you don't have to remember, right? So even if I want to derive some of those formulas like the gradient of a velocity vector, I may give you the gradient and ask you to do the calculation, or if I want you to simply use it in a problem, I would give you the formula directly, so you don't have to worry about it. So the question paper would be full of these formulas for Laplacian and so on, whatever is required. You don't have to memorize any of those complicated ones. Right? So if you know the basic principles of how to go about setting up a problem and boundary conditions and so on and solving them. We've looked at energy balance and momentum balance in great detail, energy balance with slightly lesser detail, mass transfer with very little. So the emphasis will also be like that. Maximum balance is also coupled with the momentum balance. And so we want to, for instance, calculate the viscous dissipation effects, so that you have to know how it is calculated from the momentum equations and the velocity profiles and so on. So it's all interlinked. And mass transfer will be very relatively emphasis. There will be one or two basic questions and derivations and definitions. That's about it. We focus on all the other points that have been covered extensively in the assignments. You can go what will appear as problem will be along very similar lines to what have been covered in the assignment. Derivations, whatever we have done in the class, maybe slight extension of exact real prediction might be there. Few, one or two more emphasis will be on setting up of the equation of motion of energy balance and so on. Right? Any questions on the exam? Seating arrangement will be pretty much, I guess, based on which Stewart. Anyway, I'll put it up on the board shortly. So, who is the class representative? Alright, you have to distribute this. There's still some time, so I don't want you to run away. 7 minutes are left, and should have sufficient time for you to fill out, right? And then, hold on, don't distribute it. Okay? So you have to fill it up, and you have to put it in an envelope and take it to the office, seal it, and hand it over to them, right? Because that's a pretty amount filled up.